Space, the final frontier. The stars above have fascinated humans for centuries, but we only have one real way to get off our blue marble and explore the universe: rockets. It took a lot of time and a lot of research to get the science of rocketry down to a point where we can safely launch things. In this video, we're going to answer a simple question: how do rockets work? We begin, as all physics does, with Newton. It might surprise you that we're going back to middle school physics to understand literal rocket science, but Newton's laws of motion are kind of the backbone of how rockets work. The key thing to note is that rockets don't fly in the same way as planes do, because planes take advantage of the air on Earth to fly. Rockets can't take air for granted because there's none in space. Instead, the foundational principles of rocketry are the first two laws of motion, namely, a body remains at rest or in motion at a constant speed in a straight line unless acted upon by a force. On Earth, there are different sources of friction that can bring a moving object to a stop. For instance, if something's moving on the ground without a propulsive force, the friction with the ground will stop it. Even if something is flying through the air without a force to push it, friction with the air will stop it. And the second law is, when a body is acted upon by a force, the time rate of change of its momentum equals the force. In other words, if something like a rocket shoots a big old flame out of its backside, the flame will provide an equal but opposite force and push the rocket forward. As the rocket takes off from Earth, the force provided by this combustion has to be strong enough to overcome the weight of the rocket and air resistance. But since space is a vacuum, a small push is enough to give the rocket enough momentum to fly to its destination. There's a lot more to rockets than just the two laws of motion though. Now that we've established the basics, we can move on to the nitty-gritty of how rockets work. A rocket consists of two stages designed to help it reach space in the first place. The first stage helps escape the atmosphere. As we mentioned earlier, a rocket has to overcome a few things close to the ground in order to fly. There's the gravity pulling the massive rocket to Earth, and then there's the planet's atmosphere, which is thicker at the lower level. An obscene amount of power is called for to make this launch, and so the first stage has the beefiest and most powerful engines of the rocket. On SpaceX's Falcon 9, the first stage has 9 engines. In the early portion of the rocket's launch, it has to deal with air resistance. There are two conflicting facts at play here. The faster the rocket goes, the more air resistance it's going to encounter, while the higher it gets, the thinner the atmosphere gets. As a result of these two variables, the stress on the hull and engines rises and falls during this stage. Since we looked at the Falcon 9 as an example, let's look at it once more. For that rocket's build and design, the maximum stress, or max Q, comes at 80 to 90 seconds after launch. The same is true for the United Launch Alliance Atlas V. So this is basically a matter of brute forcing the rocket through the counteracting forces in the lower atmosphere. Once that part of the launch is cleared, the rocket straight up jettisons the first stage. This sounds concerning because the first stage is big and heavy, but mission planners account for that. The goal is to ensure that anything the rocket drops either falls through the atmosphere and burns, or into a big ocean far away from any inhabited areas. The rocket also drops its fairings at this point, as well as the pointy cone at the tip of the rocket that allows it to use sharp force to aid in punching through the atmosphere and shield the rest of the rocket. Now that we've cleared the first stage, let's move on to the second stage, which involves actually getting to space. The hard part's over, and now we can take things easy. Because the upper atmosphere is much easier to get through, the second stage of the rocket has just one engine. This stage is meant to guide the rocket through to its actual destination, which can either be low Earth orbit or beyond. Along the sides, the rocket will also have side boosters, which can fire off small bursts to align the direction of the rocket. The equipment in the second stage is designed to get the rocket where it needs to go, but not necessarily bring it back. These are the essential stages, but depending on what the mission is, there can be up to 4 stages on a rocket. All these stages are usually dropped once there's no use for them. Rockets hold on to the side boosters though, because they can come in handy during the mission. They also have one other really important use. See, you might be wondering, but if all the stages are gone, how does the rocket come back? Okay, so this is kinda scary. What the crew does is use the side boosters and any other auxiliary boosters to push itself into the gravitational field of the planet, and then gravity does the rest. That's right, folks. Once your mission is over, you basically allow your rocket to fall from space back to Earth. What happens to them during this process depends on the nature of the mission. If it was an unmanned mission and the higher-ups really aren't interested in getting the rocket back, the whole thing can be designed to burn up in the atmosphere. But if there are people on board, that really isn't an option. In that case, the rocket may be equipped with thrusters specifically intended to slow the rocket's descent to the ground, or they could just have parachutes. parachutes. The old tricks still work. As for where the rocket lands, that depends on whether it was a reusable craft or not. The one and done rockets can be allowed to just fall into the sea, where everything inside will be safe, but the rocket itself will probably be permanently damaged. But there are rad systems now that allow rockets to land on a launching pad in the same vertical position from which they launched. So the mission is a success. The crew can go home and celebrate. Quick question though, dropping fuel-filled chunks of a rocket sounds bad for the environment. It would be if we left them there, but that really isn't the case anymore. The reason we drop rocket stages into the ocean now is precisely so they can be recovered. And besides that, rocket parts these days are being designed in a way that they can be reused from mission to mission. After all, building things costs millions of dollars, so it makes sense to try and protect the investments. But that doesn't fix the fact that this scares the fish. Or, more importantly, dropping such massive objects into the ocean isn't without an environmental cost, whether we recover them or not. One of the areas of rocket development right now is how to safely recover as many of the rockets as we possibly can. At the forefront of this development are SpaceX and Jeff Bezos's Blue Origin rockets. They're developing rocket stages that are capable of being remotely controlled, which would allow mission control to safely return the stages back to landing pads, at which point they can be restored and prepared for the next mission. One last question. Are all rockets the same? Of course not. Well, we've talked about the foundations of rockets and how they work. There are different types of rockets that are designed for different missions. They follow the same principles we discussed before, but they also have unique characteristics for their intended missions. One example is the sounding rocket. These are basically million-dollar paper planes that we throw into the air and allow to arc through the skies before returning to the ground. They're generally used to conduct short experiments at super high altitudes. The first stage is key for sounding rockets, while the second stage is very small. Sounding rockets have an arc-shaped flight pattern which causes them to naturally return to the ground. Then there are suborbital rockets. These are, again, used for experiments, but you'll also find these rockets used for space tourism. When you see Virgin or Blue Origin offering you a trip to space, it'll be on a suborbital rocket. As the name suggests, these rockets don't venture too far beyond the upper atmosphere of the planet, and they're equipped accordingly. The opposite of a suborbital rocket is an orbital rocket, which is what we usually think of when we think of rockets. These rockets have powerful enough stages to achieve an orbit around the planet. The last major class of rockets is the satellite ferry. These rockets have one goal and one goal only: take a satellite to a planned orbit and leave it there. Toting a massive satellite significantly increases the overall weight of the rocket, so these are massively powerful. Once a satellite is brought to its intended altitude, the mission is over. At that point, the rocket is brought back to Earth. Depending on what the mission planners want for it, it could return safely or burn up in the atmosphere. We'll also be returning to Earth now because this is the end of our class on rockets. Make sure to drop any questions you may have in the comments below, and go ahead and share some rocketry fun facts. Don't forget to like, share, and subscribe.